and to also chat more offline. So yeah, as we all know, the landscape of energy systems has changed a lot in recent years. So renewables like solar and wind has been entering into the grid. For example, in California, we have the goal of achieving 100% clean energy by 2045. And at the same time, the demand side resources, instead of just consuming energy, they're optimizing their behavior as well, including both large industry commercial loads like Microsoft, Google's, they're using AI to reduce their electricity consumptions of their data centers or even build their own on-site generations. And also we see large buildings are becoming great interactive to provide demand response or peak shaving service. And also we have a lot of undead on flexibility from storage and EVs. So with all this change, it makes our system more complex, more uncertainty, and therefore more challenging to operate and control. And my group, the focus is in incorporating learning and control with performance guarantees for power grid control buildings and general cyber physical systems. So I'm going to provide a very quick highlight of our main research project right now. And so the first direction we are working on is called stability constraint learning for power grid frequency and voltage control. So specifically, we leverage control theory to extract some structural constraints on how to guarantee stability or optimality. And then we design learning algorithm within this class of controllers to optimize performance. So I'm going to share more on this perspective in my talk today. And another direction we have been investigating is for building HVAC system and other systems governed by partial differential equations, actually. So the controller and state estimation design for these partial differential equation systems are PDE themselves, so which are usually very time consuming to solve. And to overcome this challenge, we have been exploring a new learning architecture that calls neural operator learning, so which basically generalized traditional neural network learning from vector to vector space to function space. And we are able to gain quite a lot accelerations by using this neural operator solvers while still maintain the stability guarantees. So I'm going to also talk a bit on its application to building HVAC control into this talk. And last but not least, when deploying these learning-based controllers in practice, we actually need a learned controller being able to adapt. So to adapt for potential model mismatch between simulators and the real-world system, so we require the ability of online learning or online optimization. On the other side, we want to be robust against certain disturbance, especially the disturbance are adversarial, such as in a cyber attack. So we also design some learning-based algorithms that are robust. So if you're interested in any of these directions, I'm happy to share more offline. And also I'm available here tomorrow, so feel free to send me an email if you want to chat more on any of this perspective. Yeah, sure. Yeah, I'm also available here. Yeah. So in today's talk, I will share our experience in designing learning and control algorithms for these two applications. One is power grid voltage control, and the other one is building HVAC system control. And actually, this is a real system architecture from UC San Diego, where I worked at. So this is a distribution grid architecture of the UCSD microgrid. And also, this is a real building on campus. So it's a large lecture hall, has over hundreds of rooms. We actually have published the building architecture and some real-world data in this web link if you're looking for some real-world data. So for both applications, actually, there has been many papers and research on incorporating learning for control of these systems. But while we have seen in practice, there's not much implementation yet. So there is a gap. And so I think one of the critical gap here is the system operators still, like for both the grid or building, still lacks the trust for learning-based algorithms, mainly due to they usually have no like guarantees as specific, for different, as guaranteed under traditional controllers. And also, they're not quite data efficient for this energy system applications. We don't have a tons of data, like millions simulation data as in playing games. So like, yeah, so we're requiring for algorithms with guarantees and more efficient to bridge this gap. And so I want to provide some of our thoughts on this aspect. So how can we bring in some structures to help bridge this gap? And specifically, we're going to look at two control architecture here. So one is for the distribution grid voltage control, we only have very limited computation or communication capability. So in this setting, I want to share our experience in designing just directly learning a policy. So when we learn a policy offline and deploy this policy in the real system, so we want to incorporate some structures into this policy so that we deploy it with assurance, even though we don't have the opportunity to update it online. So specifically, I will talk about encode stability. And then for building system, so these are the systems. So fortunately, maybe we have some communication or computation capability to do some online computation. So in that case, I want to share our experience in designing this model-based controller, specifically a model predictive control, MPC controller, where we learn the model and we encode the structure into the learning the model part to make it more efficient. And then we can guarantee the constraint. Basically, when we solve an MPC, we can encode the constraint here. So here is more like we encode the structure in the model learning phase. So without further ado, I'll start from the first part on the distribution grid voltage control. So suppose this is a distribution grid, and each node here is a load. So whether it's a building or a residential home. So when we have a lot more renewable added to the system during the noontime, maybe you're going to see the voltage start to increase as the renewables inject power into the distribution grid. And after work, if we have many EVs, if they're drawing power simultaneously, you're going to see this voltage drop. So actually, some neighborhood in California has facing such large voltage deviations in recent years. For example, in Pasadena, the local utility, Pasadena Gas and Electric, has reaching out to Caltech to install and investigate where to install some batteries to help solve this large voltage deviation issue. So the goal we have here is to, despite this various real power fluctuation, we want to design a reactive power controller to help maintain the voltage always at the reference value. So here is a control system architecture. So the blue layer is a physical power grid, and then the green layer is what I call the cyber layer. So the voltage magnitude in the distribution grid is governed by the distribution grid power flow model. So here, this different equations basically tells us at each node, the real power balance, right, and the reactive power balance, and also the voltage drop follows the Kirchhoff's law. And so our control action is the reactive power injection, so which are controlled by the inverter interface DERs, such as batteries or solar panels. And so basically it needs this sensing and actuation capability to sense the voltage magnitude and compute what is the reactive power injection to help bring back the voltage deviations. This problem has been studied extensively in the power system literature. So one established line of algorithm is model-based optimization. So basically we can formulate this voltage control as an optimization. We want to minimize certain cost by deciding what is the reactive power injection. So subject to the power flow model, that is a dist flow model, where some people use a linearized approximation. And also you can put a voltage constraint there because you want to make sure your voltage stay within some like plus minus 5 degree of the nominal value, let's say within 110 volts. And people have been solving centralized to decentralized optimization to decide the optimal set point of Q. So it can optimize certain desired cost. However, one caveat is we requires exact model knowledge of the distribution grid. And also you need to know the exact disturbance, which unfortunately are often unknown, especially for secondary distribution grids, like in our neighborhood. So the utility actually have no good idea about the exact topology with the up-to-date topology and also the disturbance for solving such optimization. So to overcome this challenge, another line of research follow-up is to design feedback controllers that does not require model knowledge. So for example, this is the IEEE standard for this inverter interfaced DRs to adjust reactive power. So it's a linear controller. Basically, at each time step, you measure your local voltage VI, and then you can adjust your reactive power accordingly using a linear feedback controller. And so it actually has some dead band and also saturation to make it works more robustly. So there has been research actually back to 2014 showing if you're just using this P control, like proportional control, there exists disturbance that you're not able to recover to the desired range, let's say plus minus 5%. So after that, people have been introducing this controller with memory with the integral term. So basically, we adjust the reactive power as the previous step's reactive power injection plus this proportional term. So this can be viewed as a PI control. So under this PI control law, actually it has some very nice properties. So it can guarantee convergence to either the reference point or certain range of it. And usually this phi is designed as a linear policy. So, yes.
These list flow problems or models, are they non-convex, non-linear problems, or what kind of optimization problems are they?
No, it's a linear model. So if you use a linearized power flow model, this is a linear system. If your cost is nice, you can have a have a closed loop.
Approximation of the AC power flow, right?
It is approximation of the law with a dist flow model with loss. So this model is non-linear. You have the loss term.
Right.
Yeah, you have the loss term. Yeah, the lean dist flow model is linear. So it's this basically VXQ. Yeah. Right. Great. Yeah. So yeah, but that is exactly the point. So these controllers are linear. So it can it may incur suboptimal performance when we look at the performance under the actual nonlinear system. So, and this is precisely the gap this very recent learning-based literature is trying to solve. So if you look at in the past 5 years, also since 2019, there are hundreds of papers trying to instead parameterize this controller. Still follow this like incremental controller structure, but in parameterize this change as a neural network. This UI is no longer a linear function, but as a neural network. So once you parameterize as a neural network, you can directly train your neural network parameters with a simulator. And this great simulator simulates the original dist flow model, which is nonlinear, so that the hope is to optimize the performance, perform better than linear feedback control laws. This actually, so it's very easy to test this out, and this is the starting point for this research. When I was a postdoc, I just take this papers and implement a neural network controller and see how it performs. And actually it performs very nice during, it performed very nice. So during training, it usually takes like 500-600 epochs, and then you can see it converge. And then I actually try to compare its performance. So the solid line are the neural network trained with reinforcement learning, and the dashed line are the linear controllers. So if you look at like the comparison, right, I plot like 3 different nodes under one under voltage issue, one over voltage issue. Yeah.
Oh, sorry. For those of us who don't do ML as much, can you clarify what like an epoch is in this context?
Oh, right. So basically, one episode we generate like a couple of initial conditions. I remember it's maybe 100 or less than that. And then we basically evaluate how the current policy performance on this set of initial conditions, right? And then see how our controller performs. And then we collect the performance, use that as a loss function to improve the policy parameter. And then we update the policy parameter, try it again on this scenarios. And this is how basically it works, this x-axis. Yeah. Great. Oh, yeah. Yeah. Oh, right. So the reward function, it depends on where we set as a voltage, violation, and control cost. So I believe here we in our paper, we choose to minimize the maximum voltage deviation and the square cost of the control cost. Yeah. But you can set this based on like the actual control cost of your device. Yeah.
So you mentioned there's a grid simulator. So does it mean that in this example, you know the specifications of the grid?
Yeah. So you have a simulator of the grid. Yeah. Because we're not performing this learning in the real world system. Yeah. So it's a simulator. You don't need to know the model, but you have a good digital twin or simulator of your system. Yeah. You don't need to know the mathematical expression, but you have a simulator of the system. Yeah. That's all great. So I tried that, and actually it performs very well during training. And then you can see here, so this solid line converge faster, right? Much faster than the, in general, it can recover the voltage we find shorten about 1/3 of the time compared to the optimized linear controller in this case. Yeah. So it all works very well, but then the issue we find in back to that time is when it gives some unsynced test case, that means if it give a different starting point for the voltage violation, like in this case, this is an under voltage issue. And this trained controller does not perform as nicely as in the training cases. And we find sometimes it's actually like the voltage does not recover and it's approaching to the ±5 range, but then it's kind of diverged, so it does not recover. Or sometimes it behaves so ambitiously, so we see a lot of oscillations. So basically, yeah, we find like even though how it performed nicely in training case, if it does not have these guarantees in unsynced test case, what is going to happen in real world? So we cannot trust it, and especially this instability is created by the controller themselves. Because if we're not like using this controller, right, and we're just solving the optimization problem to decide the set point, or using the linear controller, so it can restore the voltage, just suboptimal performance, right? And we introduce this neural network, hope to improve the performance, but if lose all the guarantees, it does not worth it at all. So that is basically the starting point for our research. We want to incorporate stability as a constraint into this learning process so that even for unsynced test case, we can still restore the voltage and also keep the performance improvement as I showed earlier in the training cases. And so then we start to look for methods to incorporate stability as a constraint into RL. So we saw some of the initial idea is maybe we can add more training data, because yeah, if it stays broad enough, if we say more training data, maybe it can help. But later on, we find first, this instability does not happen that often. So we need to add many training scenarios. And often, even if we add more, it still has no hard guarantees. And then also at that time, and also recently, there is this trend of this so-called neural Lyapunov control approach. Basically, we can learn a Lyapunov function, because in control, how people certify stability is using Lyapunov theory is one of the common methods. So if we can find a Lyapunov function and then incorporate this Lyapunov function as a constraint into the reinforcement learning problem, maybe it can help. But then one challenge we really find is this techniques thus far cannot scale up really for system state greater than 6 or 8 dimensions. That means like a 3-bus or 4-bus system. So it does not really work well for the power network case.
Does it offer any guarantee, like inclusion of this Lyapunov function?
It can provide guarantees, and that is why it can only scale up to this magnitude, because they use a verification technique of neural networks. Yeah. So you can actually provide formal guarantees. You sample the point, and then based on the Lipschitz of neural networks, you can say about the continuous state space. Yeah. Right. Okay. Cool.
How did you simulate the test case? The test case with the instability.
Oh, right. So how can, yeah, so basically we we just simulate. So we have 100 different initial conditions for under or over voltage, and then we basically return what is the voltage magnitude and each time step, and then we see whether the final state is within 5%, and then we pick up the cases that do not restore the voltage, and that is what I visualize in the failure case. Right.
This is constant gain, PI, right? Or already adaptive when you train.
when we train it, it's a fixed function. So yeah, because you take in the voltage measurement and then you output the reactive power adjustment. So it's a fixed function, yeah, to be learned.
Oh, that's still just linear. Okay.
Mhm.
No phi. Remember, are you going to talk about phi?
Oh no. So if we look at this phi part, so this is where we are learning. We parameterize this phi as a neural network.
Yeah.
We parameterize this phi as a neural network.
Yeah, but so your training is with that phi.
Yeah, with this phi. Phi is a neural
So it's
network.
no longer constant gain.
In terms of, it's still a fixed input-output relationship, right? But it's not like a fixed linear gain because this phi function is still learned as one fixed neural network, right? If you give me a voltage measurement, I tell you how should you adjust your reactive power.
But if I give you another voltage measurement, do you give it another phi?
Yeah, not another phi, still the same
Still the
phi.
same phi,
Yeah,
okay.
still the
So
same
it's
phi.
provable then.
It's still the same phi function. Yeah. Okay, great. And then where we find here is actually the power system structure can help us in this case. How? Yeah, actually, I think I will be willing to look. Yeah, when I talk with Maria today, actually, this monotonicity property, as you mentioned, maybe already also discovered in some previous literature. Yeah, I'm happy to read more about that. Yeah, so but one key structure, the key structure we identify here is monotone function is very important. So what I mean by monotone function is in the scalar case, it's very simple. If you have the inputs x1 less than x2, so you want the output to be, to hold the same order. So here x will be our voltage deviation, and then this f will be your reactive power adjustment, is that u function. Yeah, and in the vector case, so the monotonicity still matters. So, but in the vector sense, if you have x1 as a vector input, you system up, the response is fx1. So you have another vector input. So you want the inner product of this input difference and output difference to be positive, the inner product. So we find this is actually a key structure that we can design the neural network phi, the phi for each phi. If it holds this monotonicity structure, actually we can guarantee stability. So that is our main finding in here. So why monotonicity can guarantee stability, and how do we parameterize monotone functions? Those are the two major questions. So how do we find a stability condition? So instead of learning a Lyapunov function, actually, because in distribution grid, we have this well-constructed disk flow model and lean disk flow model. So we explore in designing a Lyapunov function by ourselves. Actually, this is a Lyapunov function we pick. So because in the distribution grid, this X matrix is positive definite. So we leverage it in the Lyapunov function design. And why we use this X in the X inverse in the Lyapunov function is the system is a lean disk flow model. This is not the lean disk flow model has a VQ, has XQ plus the external disturbance. And therefore, when you use this first line as a Lyapunov function, and when we calculate the energy difference between two steps, this X inverse and X can somehow cancel out. And then we end up with a clean condition. It's saying if your reactive power adjustment, this U, is a monotone function with respect to the V. So here the V is a vector if you have a 13-bus system. So V is a 13-dimension vector. And U is also a 13-dimension vector. So this is saying this Jacobian matrix, if it's negative definite, and also lower bounded by this part. But this part has some nice thing. Delta T is how quick you are doing the control. So if you are implement the control fast enough, then we focus mainly on this right-hand condition. This Jacobian needs to be negative definite. So what's nice about this is saying U needs to be a monotone function, and also this condition is independent of the system parameters and topologies. Yeah.
The idea of Q is actually an approximation. Is not.
Yes.
Doesn't always hold.
Yeah.
So there is an old paper by Jim Thorpe and me, which actually is intersectional circuits, which gives you conditions
Oh,
Yes,
which,
nonlinear transformation basically from b to exponential of some xi,
uh-huh.
which now after the transformation you don't need to make that approximation much. Maybe we can talk about it later.
Oh, really? That would be awesome. I think, yeah, so right now our theory, yeah, analysis is using the linear model. Right, right, right. Yeah, yeah.
So just to understand these results, so if we assume that voltage is a linear function of Q,
Mhm.
reactive power, then the Puno function has nice properties.
Right, right. Yeah, yeah.
And what is the, how do you go, I didn't understand today, how do you go from matrix conditions to scalar? Like here, this dV is just one by one, right?
No, no, it's a matrix.
It's
So
still
this,
a matrix.
yeah, this is an n by n matrix. And this is, you see, this is a matrix inequality. This is saying the matrix is negative definite. But that's a good question. So if you have decentralized controller, then if you think about this Jacobian, it's a diagonal matrix. Then in order for diagonal matrix to be negative definite, it will be sufficient to have each element, diagonal element, to be negative, right? So that kind of recover if we have a linear decentralized controller and the controller gain is negative, right? So that will satisfy this stability condition.
Not decentralized, this is still decentralized.
Also, this can handle various communication architecture. So if your system has no communication, so you can do decentralized control, right? Then each node have a so-called monotone neural network. So only takes node of VI and decide node of UI.
Oh, is that true?
Yeah, yeah, that is
Because
true.
we still have full matrix, we have still full Jacobian. How do you go to diagonal now?
Oh, so that very much depends on for each nodal controller what information you takes in, right? For example, if you have no communication, it's a decentralized control, then each UI only depends on VI. So that's when you have a diagonal matrix.
Okay, we can talk about that because it doesn't follow straight from X is a full matrix, right? So in the Lyapunov functions, so how do you go from there all the way down to controller by controller in the conclusion?
So basically what you say is that when we don't have communication with others, and we only rely on ourselves, then we have diagonal.
Yeah, yeah, exactly. That is what I'm saying. If we don't have communication, then this Jacobian is a diagonal matrix.
That's not true at all. They physically affect each other. Come on, guys.
Oh, right. So because it shows up in this, yeah. So in the end of the day, yeah. So when we consider the dynamics, it has impact, right? Each one affect each other. Yeah, exactly. But right. It's because when you derive the v, yeah, that is why in this Lyapunov function you have x inverse, actually, because in the lean-dist flow model you have x, right? Yeah. So, and then when you actually derive this vt plus 1 minus vt, you can do when you expand this, you get this term. And when you look at this term, yeah, it is, so you get this condition. And this condition, right, this condition is saying first this is need to be a negative definite matrix, right? And then when your control step size is not that small, then your network matters because you see in the lower bound you have an x inverse part, right? So if delta t is very, very small, then we're saying this bond is super, super loose. So then we can only focus on this part. And then if you look at this part, it can support any kind of communication architecture. If you don't have any communication, this is a diagonal matrix. So
I don't understand.
right.
Some people understand. How do you go from matrix condition to actually claim now that if that matrix, just because you are just doing decentralized control, becomes diagonal?
Oh, yeah.
How do you make sure that all diagonal terms meet that condition? Because on the left-hand side, you still have full matrix, right? 2 over delta tx inverse is full.
Oh, right. So this is saying when your sampling time delta t is very small, then if this bond is very loose, if we only look at this side of condition, right? So
Oh.
yeah.
Okay, but the real network
Mhm.
effect is on
Is on the left side, yeah. So you
Yeah.
just need to actuate fast enough. The otherwise, the real network constraint is on the left side.
But then comes the real question, and the real question is, you really are not talking about stability here.
Right, I think that is
Can you explain to people what
right,
you're
right.
really doing?
Yeah. So I think I want to clarify a thing. I think that is for this. So dynamics is introduced by the controller. So I think that if you look at the disk flow model, right, this is a steady state analysis. This is a power flow model, right? And what brings in dynamics in this case, in all these literatures of feedback controller, is this controller introduced dynamics, right? Because if you look at the power flow equation, that is a steady state analysis, that is a power flow equation. But then your controller has memory, right? So that is how it couples. Yeah. So when you combine the power flow.
This is under the assumption that real dynamics are stable. I think that you guys better spell that out, because you can have things blow up in inverters, and this doesn't guarantee.
Right. I think an important step is to incorporate the inverter dynamics also into the system dynamics loop, because right now it's only the network, the power flow equation, and then your controller has this internal state. Yeah, because your controller is has a memory, so that is a state basically. So that is how the combined system, the closed loop system with controller, has a dynamics. The dynamics is induced by the controller.
So just one.
Mhm.
I worked in this area early on with EDF. They have this automatic voltage control actually implemented in, not with ADRs, but it works, right? So if you look at Q increment, Q minus QT minus 1, that's an increment, this increment between two reactive power controllers.
Right.
So it's basically increment in error that you want to control. That's a function of increment in reactive power, and that's integral control.
Mm-hmm.
If you look at it from the real dynamics point of view. So we cannot prove anything for integral control in powers, in dynamical systems. There are no provable things. So if you didn't like primary dynamics and you just slap on it this integral controller, then you're applying integral control to very fast dynamics. And we know with LQR and everything that you can actually stabilize P proportionally.
Mm-hmm.
But PI, there are no theoretical results which tell you, that what are the conditions if I have integral controllers applied? This is, for example, why people do automatic generation control and so forth. They don't lump together the stabilizing and integral control into one. So that's the real detail, but I think it could actually cause all sorts of issues. So we talk about that later.
I see. And also, I think I'll follow up on where you said about the nonlinear model. I think that is something I'm really interested in, to generalize this analysis to the nonlinear part. Yeah. And then I think I talked about why the monotonicity of the control U, right, with respect to V can guarantee stability. So next I want to talk about how we parameterize these monotone functions. I think that is a very interesting part. So if we recall in your convex optimization class, maybe you have learned about this, the gradient of a convex function is monotone. So this is because if we have a convex function, right, if we approximate the value of fy and this point fx, actually this is the under approximation of the function value. And then if you look at the function value of fx and you approximate by the gradient and y, right, this is a lower approximation of this. And then when you sum up actually these two equations, actually you find this gradient of the convex function is a monotone function, right? Because if you add them up and you find the gradient of a convex function, actually satisfying the vectorized monotonicity condition we defined before. And that is how we parameterize these monotone functions, actually. So we first parameterize a strictly convex neural network. There are so-called input convex neural networks from Zico-Carter's group back into 2017. But then we straightened this condition to be strictly convex, because when we take the gradient, we don't want to have 0 case. We want it to be strictly increasing. And how we did this is basically you can restrict all this weight, W1, W2 until WK, to all be positive. And then your activation functions to be strictly increasing, right? And then we can use the class of soft plus activation functions. And in order to improve the representation, we add some direct connections. And these direct connections have no restrictions on the signs. And, oh, right.
How do you constrain, or what kind of optimizer do you use to constrain the weights to remain positive?
Oh, actually, in PyTorch, you can just define this weights to be non-active. There is a function. And inside, I think they either use projected gradient descent or some other clipping function. But there is this line you can just add.
Did you consider changing the gain with the different voltage vector power? The phi I, like you fix the phi I.
Right. We are learning this phi I functions. Each phi I is the So I'm going to show you like how we are learning this according to different communication architecture. But in the decentralized case, each node has learning a phi I, and this phi I is a single input, single output neural network. And then when we have communications, a group learns a monotone neural network.
So for us who don't know much learning, is this phi I, can you write it ever as an explicit?
So this is basically how we construct the convex neural network part. So you take this V, and then this is the expression. So you have some intermediate layers, like Z1 is just a linear combination of the input plus intersect term, and then pass through this activation function. And this activation function sigma has an analytical expression, depends on what activation function we use here. So this is how you get Z1. And then for Z2, you basically take Z1 and then do the linear combination again, and add this intercept and pass through the sigma again. And then you're doing this multiple times until you get the output Y. This is kind of the most simple neural network architecture here.
And how is that related to phi?
And then that is how we parameterize the convex neural network. But where we want is monotone neural network. So we need to take the gradient, because the gradient of convex functions are monotone. So where we really take as output is we will take the gradient, right, of Y with respect to the input. So this is our control action U. And this is what the phi part, because you have Qt as a previous time steps rectifier injection. The Qt minus 1 is a previous time step. This is a current time step. This is a phi part, right? And phi part is represented by this neural network.
And just again, I think it's really important for proving. So this dy dv is not dependent. It doesn't change the stages. You learn it once, right?
Yeah.
Okay.
Right. We just learn it once. This is a fixed function. It's not like, for different V, we pass the same function and evaluate what is a U.
So it's product of all these, no? It's not composition?
It's a composition, not only matrix product, but also some nonlinear activation. This is showing here, right? So in each of the layer, you have the matrix product, and also pass through the nonlinear pass through the sigmas. Let's see. Right.
So does it depend on activation function?
Yes.
How much?
Right. So because in order for this to be convex, we need a convex function composition rule. So basically, the inner side function needs to be convex, and outside function needs to be convex and non-decreasing. So we only use convex and non-decreasing activation functions.
Can you use ReLU, or does the gradient disappear?
Right. We don't use ReLU. So we don't use ReLU. So we use soft plus, because if you use ReLU, the gradient can be zero. Right. Because there is this all flattened part in ReLU.
So because they're using the gradient on the neural network as the function, like an approximator, which means that when you have to update the neural network, you have to compute a very high order differentiation without slowing down your training process.
It's fine because you only have second order derivative. And also, I think this is very common if you think about, if you are familiar with the so-called physics-informed neural networks. Yeah, they have a data-driven solver of PDEs, right? So they sometimes need to evaluate even higher order derivatives.
Like with PyTorch, it can be very suffering to do that, but with JAX it's okay. But what kind of like which the framework do you use like to proceed to work?
We use PyTorch and we actually have our code. Yeah, and if you want to chat more about this issue, I'm happy to chat more. Yeah. So, but this is how we parameterize this phi function. We're using this monotone neural networks, and then I think this is a communication network part. I think this will clear up many questions. So, for example, if it's decentralized, each node, only receives its local voltage measurement and decides its local reactive power adjustment, then each node needs to fit a strictly convex neural network and use a gradient as a controller, right? Because that guarantees monotonicity. And then if it's a full communication distribution grade, so then that is nice because we can just gather each node's voltage measurement and fit one strictly convex network and use its gradient as a control action, right? And in that case, this Jacobian partial U, partial V is not a diagonal matrix. It's like every element, probably it has every element depends on each other. Yeah, this is a centralized communication case. And then if we have partial communication, for example, some nearby nodes can talk with each other, then those group of nodes, they form a strictly convex neural network, and we take the gradient as the controllers for this group of nodes. This is how we call it communication embedded monotone network structure. So to cope this controller design with the distribution grade communication network structure.
In reality, which of these architectures really happen? Is it like full communication in reality?
In our simulation, we use the decentralized case because there is not much communication capacity available right now, especially in secondary distribution grade. So this is our implementation I'm going to show in the next.
Communication in terms of control, not in terms of power flow. I agree. So there is still some interaction between nodes in terms of the power flow and the reactive power and so on and so forth. But you use decentralized because you want to control them as a...
The control is only based on nodal voltage measurement to decide the nodal reactive power adjustment. And this is how we implement it. It's a decentralized implementation. So we have using the UCSD DR Connect testbed, they have the RTDS hardware in the loop simulator. Basically, we train this controller offline and load it into a Raspberry Pi in each of the nodes. And then each of the nodes interact with the grades being simulated in the RTDS form. And then the DR Connect team help us with this implementation and evaluation. So where we simulate here is two voltage disturbance. One is an under voltage issue, and you can see how different nodes collaboratively restore the voltage into this green band, which is a plus minus 5% of the nominal values. And also here we simulate again another high voltage issue earned around 8 seconds. And then within about 2 seconds, it brings back the voltage to this nominal range. And then also we compare how this monotone neural network compare with the linear controller and unstructured neural network controller. And this is so some of the nodal controller curve looks like. So you can see here, this blue dashed one are the linear controllers. So it has different slope in different nodes because those gains are optimized. And then the orange line are the unstructured neural network. It can have crazy shapes and sometimes too ambitious, which is causing some of the oscillations here. And also the green line is our monotone neural network. So you can see it can maintain the monotonicity, but also it has some nonlinearity in different regions to improve the performance compared to linear controllers. And we have also extend this framework to not only restore the voltage, but also restore the voltage to the optimal, we have a desired equilibrium point. So we want to restore the voltage actually to the solution of the economic dispatch problem. And also we have collaborate with, so this work is collaborate with colleague at UCSD Houghton Cottis. And also we have been collaborating with Professor Patricia Gonzalez, also on extending this monotone neural network for frequency control. But we consider here the state will be frequency. Each node measure the frequency and decide the real power adjustment. But we consider more special case because of different renewable penetration ratio. We have a different inertia in this case. How could we extend the monotone network to this case? And as a summary, so in this part, we kind of combine physics and learning. So the physics prior is in the form of policy structure. So we have derived the monotonicity implies stability derived from control theory. And then we encode this structure into learning and just using neural network as a flexible parameterization of these monotone functions, right? And if I'm going to compare in a sense, so I want to draw two axes. One is stability, one is performance. So linear controller is guaranteed to be stable, but it may not optimize the performance for the nonlinear system original. And the neural network controller can optimize performance, but it does not have this stability guarantees. And where the monotone neural network here, because it just generalized the linear control law to a more generalized monotone structure, and so it can maintain the stability guarantees. And also because it's more flexible, it can be piecewise linear, right? And also have nonlinearity in some regions. So it's more expressiveness, so it can improve the performance.
Any optimality guarantees? Because this is sort of like I guess like a multi-agent setup, right? So are you able to derive guarantees also on optimality of the controller, not just stability?
Yeah, that's a very good question. So actually, the guarantee, the optimality we guarantee is the final point we converge to. So that point will solve economic dispatch point problem. But we don't guarantee in the transient in the process, right? Yeah, it will solve the we don't have guarantee in the process where you drive back the voltage. Yeah, in that intermediate process, it does not necessarily recover the optimal of this because reinforcement learning training, you have no guarantees of finding the optimum. Yeah, but where we can guarantee is after you converge, right? Because we have stability guarantee, so we know you will converge, right? And for this, so we will guarantee the final Q star and V star will solve the economic dispatch. Thank you. Any other questions here?
Is this an unbounded control, which means that you can provide enough reactive power?
So this is a great question. So this is a great question. So actually, in this paper, we put the reactive power constraint Q bar into the loop, and how we do it is we use a control barrier function. So we project the reactive power change so that you stay in the bond. But for the work so for this part I presented, so there is no reactive power constraint. But we can accommodate reactive power constraints in this follow-up paper. Yeah. Right, but that's a great question. Yeah. How did you? Right. So how we basically put a reactive power constraint QT is less than Q bar, and then every time when we update the U, right, we if the neural network suggested is a neural network suggested action plus the QT minus 1 exceeding the bound, so you just do like within the limit.
So we just had actually that discussion in the class today. So you lose controllability at the secondary level. The minute Q reaches saturation, Q max, then your voltage beginning to behave like reactive power load, and voltage just drops. You no longer have that control.
Right.
So there is no magic here.
Yeah, exactly. So you need to make the assumption that your original problem, right, is because you originally solved basically. Let me find this optimization problem. So if your original problem is feasible under the reactive power constraint, you can do that, right?
Sorry, what?
So if this optimization problem have a feasible solution for Q less than Q bar, right? So because we're trying to restore the voltage where the voltage has a constraint, but also here you have the reactive power constraint, right? If this optimization problem is feasible, then in the control stage, we can find that point.
But limited on Q.
Yeah. So you need to ensure that this optimization with a limit in Q is feasible.
How do you do that? That's the whole problem.
Oh, so that is the assumption. So if this problem is feasible, then you can still guarantee then you have the controllability or the stability part. Right. If this problem is not feasible, I think there is not much you can do. You cannot restore the voltage, right? So if you have reactive power constraints, you need to show this problem. The assumption is if this problem is feasible, then the feedback control we can do can also restore the voltage. But if this problem is not feasible, then you are limited by how much control you can do, right? Either you have, so you will end up with voltage violations.
This is very serious because that loss of controllability of the max has been cause for several blackouts, worldwide voltage collapsing. But I think you can actually get around because you end up, let's say, if you have M controls on M locations, now you're just ending up with M minus one, and first one hits the limit. And then you may still have controllable system at the secondary level. Maybe we can talk to a piece of paper on that.
I see. You mean your other controllers has more capability?
They pick up, and that's one of the very big questions with IBRs and all these power electronic stuff now. Yeah.
I see.
So you may not need all of them, right, to still keep controllability.
I see. But I think you still need at least this with the Q constraints. This problem needs to be feasible. Yeah, in order to.
With all Q constraints.
Yeah. With all Q constraints, this problem needs to be feasible.
Feasible with M minus one. That's what I say. Like you have M controllers. If you go one for one decentralized, there is not much hope.
Oh, I see.
Oh,
I see. You're not saying this problem may not need to be feasible, but if you remove one of the controller, it becomes feasible, right?
You still have controllability conditions satisfied in that.
I don't know. Yeah.
The references on that too. This is a very old problem that now we are rediscovering because of machine learning. And so I'm trying to figure out myself. I asked that question. With and without machine learning, I think it would have been nice to compare with.
Oh, the centralized LQR?
Yes.
Yeah. Yeah, I remember that question.
Necessarily. In France, these control schemes worked on what they call pilot points. In each region, you have one measurement, and then you control. And there are 19 regions, so it's not just centralized fully. It's really a very, very important problem in power systems. But how many controllers, which heat saturation is a real issue. Anyway, always work for more time, more work, right? Okay. Any other questions? We almost.
Yeah.
Still on this case study.
Oh, yeah, sure. The case study, you mean the result? This result?
Yes. So in this network, is that mean you have 9 controlling points that have secondary control in this small grid?
Oh, we actually have controller in all the nodes. This is a 13-bus system, and this is a 13 controller. Yeah.
But you are considering a secondary control, and you consider all the control points have the controllers for them.
Yeah, for now, yeah.
Yeah, in this test case. Yeah.
Okay.
And also, but in the paper we have much fewer controllers. Yeah, for example, in this 56 node system. Yeah. So in this case, we only have 5 controllers. Yeah. So yeah.
But then do you have provable case then? You don't.
No, yeah, in order to prove we can only guarantee stability for the node with control. Right.
So when in this case,
If it's decentralized. If it's, yeah.
so in this case, when you have only 5 controllers, are your feasibility conditions still satisfied with a certain bounded reactive power in your methodology you showed just now? Because if you only consider 5 control points, so and just now your methodology, you assume that your solution must be feasible and also there have some bounds for the reactive power.
Right,
Is
right.
that still
Yeah,
satisfying?
you need communication. So if you don't have communication, you cannot restore the voltage and on node. But if you have communication, then you can satisfy that vectorized monotonicity condition, right? Then you can guarantee recovery.
But you,
Maybe we can have all other questions after we wrap up.
Yeah. Okay, cool.
So,
Yeah,
yeah.
sounds good. Yeah. Okay, cool. I think I'm actually running out of time, so I won't talk about the second part on building control actually. So the problem we're solving there is basically we want to incorporate air quality conditions also into building control rather than only thermal control and energy saving. So we're yeah, but I think I will wrap up here. And if yeah, here is my contact. And if you have any questions or if you want to chat more, feel free to just reach out and I'm happy to chat more. Yeah.
Thank you very much.
Thank you.
More about the building control.
Oh, sure,
Because it's really simplified introduction.
Yeah.